For nuclear magnetic resonance spectroscopy, when you are interpreting the spectrum, there are three things that you need to consider. The chemical shift, which gives information about the type of hydrogen, the environment that it's in. Integration, which tells you the number of hydrogens. And the splitting or coupling, which gives information about how things are bonded, what the neighboring hydrogens are. So we can take an example. We have a spectrum here. Addressing the chemical shift first, we would look at the peaks and then correlate those peaks with a correlation table. We have certain groups that show up in particular regions. For example, if we have peaks in this region about 0.7 to 1.8 ppm, this is saturated carbon hydrogens, in particular the hydrogens. Typically between 2 to 2.7, we see CH that's next to a double bond, so allylic or benzylic, or the CH next to a carbonyl. Peaks out around 3 to 4.5 is typically where we see our alkoxy, or aromatic region, out around 6.5 to 8 ppm. So we would apply that to our spectrum. So starting the high frequency range, we have some peaks out here around 7. We have 2 peaks. This is the aromatic region. So we know these are hydrogens that are on an aromatic or a benzene type ring. Next peak over, around 3.7. This is the alkoxy region if we look in our correlation table. So this would be a hydrogen that is next to an electronegative atom such as an oxygen or a halogen. Moving over to the next one, about 2.7 ppm, this is the region where we see allylic and benzylic hydrogens. So this would be a hydrogen that is next to a double bond of some sort. In this case, since we have an aromatic ring, these are likely benzylic, but this could be also next to a carbon-carbon double bond, carbon-oxygen double bond, something of that sort. And then next peak over, about 1.2, we're looking in the region where we see our typical saturated alkanes. Right, the next thing we would look at would be the integration. Integrations do need to be whole numbers. We have fractional numbers here. So you can either, if you know, for example, that this is a CH3, you could multiply it by some factor that would set this to 3 hydrogens, and then multiply all the peaks by that same factor. If you have no idea what any of them are, you can simply divide each peak by its smallest and get a ratio that way. So our smallest here is 0.83, so we would divide all of the peaks by that, and we would get 0.66 divided by 0.83, we get 2 hydrogens. And this is 2 hydrogens. This then turns out to be 3. Of course, with computers, we can have the computer do that automatically by setting the value for one of the peaks, and it will automatically adjust all of them. And at that point, we know, for example, that this, because of integration of 3, is a methyl group, a CH3. Integration of 1 tells us this is a CH. Integration of 6, we cannot have a CH6. Carbon can't have more than 4 bonds. So the logical or likely explanation is that we have 2 methyl groups, 2 CH3 groups that happen to be chemically equivalent, and therefore they show up at the same peak. Also moving out to the aromatic region, so out here, integration is 2, but again we have to think like a chemist. You cannot have a CH2 in an aromatic ring, so this would be 2 CHs, 2 individual carbon hydrogens. In particular, again, the peaks are from the hydrogen, since this is proton NMR. But we have 2 hydrogens for this peak, and then 2 separate CHs for the other peak as well, telling us that in the aromatic region we have a benzene ring with 4 hydrogens total, meaning it's a disubstituted benzene ring. The third thing we look at is the splitting. We have typically for our common splitting patterns, and there are some that are not so common, ones that you don't encounter as frequently, and we won't talk much about those. But the common ones, the number of peaks is going to be one more than the number of hydrogens. And those common splitting patterns are things like a doublet or triplet, quartet, quintet, sextet, etc. A few things to note about these is the peaks are symmetrical. The spacing between the peaks is uniform. So for example, with this quartet, the space between the outer and inner peak is the same as the distance between the two inner peaks, or the same as the distance between this outer and inner peak. If you have a peak that looks like this is not a triplet. First off, because the spacing between those three peaks is not uniform. Also, these peaks have symmetry to them. For example, with a triplet, the two outer peaks are half the size of the inner peak. Or with the quartet, the two outer peaks are roughly a third the size of the two inner peaks. There's a regular pattern. And again, for this peak, we do not have that. This peak is significantly shorter, but this one is significantly taller. We don't have that symmetry. And so that's a second reason this would not constitute a triplet. So if we apply that here, our first peak is a singlet, which means there are 0 neighboring hydrogens, which of course we should have expected. If you remember, this was a CH3 from the integration. The chemical shift told us it was bonded to an oxygen, so there can be no neighbors. Going to the next, or this first peak here, of course it helps to expand that, and we can see then this is a doublet. 2 peaks, meaning then that is bonded to 1. So remember, this was 2 CH3s. And the splitting tells us that they are bonded to a methine, a carbon that has 1 hydrogen. So we have this pattern. And so this is the methyl groups of an isopropyl group. Next peak, again, helps to expand it. And we can see then that we have 1, 2, 3, 4, 5, and then small ones here, 6, 7. So we have 7 peaks. That makes this a septet. That means also that we have 6 neighboring hydrogens. Remember, the integration was 1, so this is a CH. If it has 6 neighbors, the most likely explanation is it is bonded to 2 methyl groups. And that would account then for the septet. It has 6 neighbors. And so we are again looking at an isopropyl group. And it is this CH that is giving rise to this peak, and this doublet is resulting from these 6 hydrogens. So this tells us how things are bonded. Again, this was 2 CH3s. The splitting told us it is bonded to a CH. And in fact, we have only 1 CH in our spectrum, and so those two are bonded to each other. And so we have this part of our puzzle, or this part of our structure, so far from the spectrum. So moving out to the aromatic region, if we expand it, we get these peaks here. There are 4 peaks, but these are not quartets. Again, a quartet is a 1-3-3-1 pattern. These outer peaks are not a third of the size of the inner. Also, the distance is not the same. These 2 inner peaks are very close together, whereas the outer and this adjacent inner peak, or this one here, are not equally distant. And so this is not a quartet. We would refer to this then as a multiplet, and we don't really know exactly what the number of neighboring hydrogens are. Some of you may have studied in lecture that this is in fact something called a doublet of doublets. Just briefly, if you're interested, you don't need to understand this, so if you don't follow it, this is fine. But a doublet of doublet arises when you have some hydrogen signal that's being split by one neighbor into a pair of peaks. This gives you a doublet, but then a second hydrogen splits it again, but splits it by a different coupling constant, and so you end up with a pattern like this. And then your spectrum is that. And so you get this is referred to as a doublet of doublets because you have two neighbors, but they are splitting that one hydrogen by different coupling constants, and so you get different spacing. Again, if you don't follow this, it's not important. What is important is to recognize that we have two peaks, each with an integration of two hydrogens. They're in the aromatic region, meaning that we have a di-substituted aromatic ring. And given that there are only two signals, the only way we can do this is with a para-di-substituted ring. If you consider the other options, one would be to have our two substituents in a ortho pattern, but that would leave 4 different hydrogen signals. We do not have symmetry, so this hydrogen is not the same as this. And likewise, these two are not. So we have 4 different hydrogens, and we would end up with 4 peaks. Whereas in the para-di-substituted, we have a plane of symmetry. So these two hydrogens are equivalent, and these two are equivalent, and hence the 2 peaks. You could also have a meta-disubstitution, and again, we lack that symmetry if we have our substitution this way, and we end up with 4 unique hydrogens. This one is different from the others, and these two are also different. One's adjacent to X, one is adjacent to Y, and of course this is different as well. So we would have 4 different signals, each integrating to 1, if we had either the ortho or the meta substitution pattern. So we know this is a para-di-substituted aromatic. So at this point, we have these pieces of the structure, and all that's left is to assemble them, and there's only one way to do that. This aromatic ring is bonded to 2 other groups, and we only have 2 others. So one of those carbons is bonded to the methoxy group, and the other is bonded to the isopropyl group, giving us this final structure. This is the sort of analysis that you need to do when you are analyzing your spectrum, and you need to report this. Walk through this procedure, not quite in this detail, but you do need to walk through it when you are writing up your conclusion. All right, so let's talk about reports. First, reports need to be 1.5 or double spaced. Leave enough room for me to leave comments and suggestions for your report so that you can improve them after each iteration. And so for the report itself, start with the abstract. When you're writing an abstract, you need to consider first, what was the objective or objectives that you were trying to accomplish with this experiment? Second, how did you try to accomplish the objective? Third, what were the results? And fourth, how do you know? So let's approach this with the Grignard reaction. First, what were the objectives? You actually had 2 objectives. The main objective was the synthesis of the alcohol. Now, when you are writing your abstract, you do need to be specific. You can't simply say synthesis of an alcohol. You would need to specify the specific alcohol. So if you were trying to make, for example, 2-methyl, 1-phenyl, propane 1-ol, you would need to write that out. You can't just say alcohol. But we did have a second objective. Since we were trying to do this via a Grignard reaction, you also had to synthesize the Grignard reagent. So those are the two objectives. So the second part of the abstract, how did you try to accomplish the objective? We did it specifically through a Grignard reaction, so you do need to mention that. But there's more than one way to do this via the Grignard, so you need to list the specific reagents that you used to make that product. So for example, to make the alcohol, you reacted the isopropyl Grignard with benzaldehyde. So we don't simply say a Grignard reagent with an aldehyde, we name the specific ones. But also, again, you had to make the Grignard reagent, so you would need to specify that was synthesized by reacting 2-bromopropane with magnesium metal. And again, we don't just say an alkyl halide, we specify the specific one that we used. So we are identifying our reactants by name and the reaction type. So 3, what were the results? First off, did you make alcohol? That is one result. Were you successful? The other would be percent yield. And this should be true for every reaction you do. Did you make your product? What was the percent yield? Now, depending on the experiment, you may have another objection. Like for the Wittig reaction, you also wanted to know the stereochemistry. Was it the cis-trans or the product? And so you would include that as well. And then finally, how do you know? And for the Grignard reaction, we used two methods. We analyzed it by IR spectroscopy and proton NMR spectroscopy. Now, when you write an abstract, it is not written as a list like I have done. You do this in paragraph form. And you write it as what you have done and how, without putting it in a bulleted list sort of like I have here. So it would be written in paragraph form. So an example for an abstract might be something of this sort. 2-methyl, 1-phenyl, propane 1-ol was synthesized by a Grignard reaction between isopropyl magnesium bromide and benzaldehyde in 48% yield. Grignard reagent was synthesized by the reaction of 2-bromopropane and magnesium. The product was analyzed using IR and proton NMR spectroscopy. A few things to note here. First, when you are writing a name, the locant, something like this 2 in the 2-methyl 1-phenyl propane 1-ol, this tells a location of that substituent. These are not capitalized. In this case, we're using a number, and obviously you can't capitalize numbers, but sometimes you will have something like a para-methyl as part of the name, and the locant here is the P, which stands for the para position of an aromatic ring. Again, that is not capitalized, but the first letter of the name is. And so the M for the methyl is capitalized. Likewise, for this example here, that M is capitalized. Since the 2 is part of the name, it is okay to use that as the beginning of a sentence. We don't start sentences with numbers, but this is not considered a number. This is considered part of a name. So let's consider the parts of the abstract. I mentioned objective. What were we attempting to do? Well, we were attempting to synthesize the methylphenylpropanol. And notice that is being stated here at the very beginning that the product was synthesized, and we're telling how it was accomplished by a Grignard reaction between the isopropyl magnesium bromide and benzaldehyde. And also, the second objective, Grignard reagent was synthesized by the reaction of 2-bromopropane and magnesium. So we're listing our objectives. We are also giving the results. We are stating that the methylphenylpropanol was synthesized, and we are giving the percent yield. They don't have to be in the order that I listed: objective, how, results, how do you know. You can list it in any particular order, provided it makes sense and it flows when it is being read by the reader. And then, of course, how do we know that we made the product? Well, we analyzed it using IR and NMR spectroscopy. So this accomplishes the objectives of what we were trying to do, how we did it, and how we know what our results and what, of course, the results were. Notice that we do not go into any details. I don't mention how much product we were using. I don't talk about whether or not it was refluxed or for how long. I don't talk about how it was isolated. All of that will be in the procedure if the reader is interested. This gives a synopsis of what was done, how it was done in terms of the reactions, the reaction type, what the results were, and how the analysis was conducted. It's short, it's simple, it is specific. We don't just say an alcohol was synthesized, we name it. We don't just say an aldehyde was used, we name the specific aldehyde. So this is an example of an abstract. We do not get into procedure. We do not get into any real discussion. We don't talk about IR and NMR results. We simply state that we use those to make the determination. The next part of the report is the chemical equation. You should all be familiar with this by now. You do need to use some sort of drawing package, and you do need to report all reactions that you performed. You may have in the readings reactions that you did not do. You don't need to put those in, but the ones that you actually did. So for example, in this one, you would need to show the reaction of 2-bromopropane with the magnesium to give the Grignard reagent. And you had a second reaction where you reacted the Grignard reagent with your aldehyde to make the alcohol. Technically, this is two separate reactions. You initially get the alkoxide. So you initially get this ion pair, the alkoxide, and you only get the alcohol after you acidify. So when you are writing the reaction, you can do it this way, or you can write this as 2 steps over your arrow. By having that 1 and 2, 1 for the ether and then 2 for the phosphoric acid, you are showing that these are separate additions. If you write it without the 1 and the 2, if you write it like this, you are implying that the aldehyde, the Grignard reagent, the ether, and the phosphoric acid were all present at the same time. But that was not the case. In fact, if you had phosphoric acid present, you would never have made the alcohol. You do need to denote that these were separate steps, and you can do that by putting a 1 in front of the ether, since that was present during the first step, and then 2 showing that the addition of phosphoric acid was a subsequent step. And then you don't need to show this intermediate alkoxide. So either method is acceptable, but of course make sure you also show the reaction to form the isopropyl magnesium bromide. Procedure. Third person passive voice. Written past tense, of course, everyone seems to have that, so I won't belabor that point. One thing that is being missed is that when you report quantities, you always report the measured quantity first. So if you weighed it, you would have something like 0.647 grams, but then afterwards you would have in parentheses the number of moles or millimoles that you had. And then of course the reagent. You do need to specify what you were using. Enough detail for someone at your level to repeat what you did. A person at your level should know what a reflux is, so you can simply say that the reagents were combined and heated at reflux. You don't need to specify or describe the reflux setup or addition under reflux, which you used. You can simply state that you set up a addition under reflux setup, and you don't need to elaborate. A person at your level knows what that is. Or when you do an extraction, you can simply say that the solution was extracted with 10 mils of ether. You do need to specify what solvents you're using, because you can do an extraction with any number of solvents, and the volume that was used. But you do not need to describe the process of extraction. When you say it was extracted, a person at your level should know that you combined the solution with 10 mils of ether in a separatory funnel, that it was mixed, that the layers were separated. All of that is implied when you say extracted. Or washed, same thing. Do not begin sentences with numbers. So for example, if this was benzaldehyde, you would not start your sentence with 0.67 grams of benzaldehyde and then the rest of the sentence. You don't want to start your sentence with a number. You can reword the sentence so that it doesn't begin with a number. In a flask, 600 milligrams benzaldehyde. For 10 minutes, mixed. And refluxed they were. No, we do not write procedures in Yiddish. You do need to use proper grammar. You can simply write aldehyde and then in parentheses give the quantity, 6.47 grams, comma, 7.21 millimoles, and then state what you did with that. You can start with the name of the compound and then continue. And again, if you are using a substituted compound, for example, if you had parachlorobenzaldehyde, The P is not capitalized since it is specifying where that chloro is, but the C here is capitalized. Calculations. You need limiting reactant, and probably the best way to do that is to simply take each of your starting materials or each of your reactants and calculate the theoretical yield of product. That for each starting material. If you have 2 of them, you would have 2 calculations. If you have 3 starting materials, you would have 3 calculations. And then whichever one of these gives the least amount of product, that is your limiting reactant. And in fact, at that point, you also have your theoretical yield calculation. And you don't need to write that a second time. If it turns out that this is your limiting reactant, this is also your theoretical yield calculation, and so you can simply use that. And then, of course, percent yield, actual over theoretical, times 100%. But when you are calculating your theoretical yield or limiting reactant, always show or always start your calculations with the amount you measured. So the amount of starting material, if you're dealing with a liquid and you measured volume, you would start with the volume. If you weighed it, you would start with mass. But you would never start with moles since you do not measure moles. That's a calculated value. So start with grams, calculate moles, and then from moles you go to grams of product. One other point with the calculations, do use proper significant figures. I have an example here where you see a limiting reactant calculation. In this case, it stopped with moles rather than going on to calculate theoretical yield. But according to this calculation, we have equal amounts of both reagents, and so either one can be used as the limiting reactant. In actuality, however, if you use proper number of significant figures, you will find that it is in fact this first reagent, which is limiting reactant. We have less of it in terms of moles. This is not obvious or evident if you cut off at one significant figure. So make sure you calculate all the way out. It does in fact change the theoretical yield as well. May not be a big change, but it is a difference. So always use the proper number of significant figures for your calculations. So discussion and conclusion. This is where you present your data. You need to analyze or interpret your data, discuss it, draw conclusions. All spectral data must be presented in tables. So if you have an infrared spectrum, there should be 3 columns. The first will be wave numbers. Second, characteristics. Is it broad peak? Is it a sharp peak? Is it a strong absorption, a medium or weak absorption? And then a conclusion for that. What kind of bond type is this depicting? Something to note here, if you have a single peak, you give a single frequency. If there are multiple peaks, then you would give a range. So for example, an alcohol peak tends to be fairly broad, but despite that, it is one peak, so we give one frequency. On the other hand, for CH, you will often have multiple peaks, and you might have something that looks like this. And rather than give a frequency for each and every peak, you would simply give the range. Now, when you discuss it, the discussion should be able to stand independently of the table, meaning I can delete your table and still understand what you are talking about. So tell me what is present in the spectrum. For example, there is a strong broad absorption at 3420 wave numbers, and then tell me what it means. This is characteristics of OH bonds, and then draw a conclusion. This indicates my product is an alcohol. Do that for basically each column that is in your table, or excuse me, each row that is in your table should have a sentence or a little paragraph describing it. For IR, it is often important to also talk about things that are not present, which might be if the reaction hadn't gone. For example, your starting material was an aldehyde. So the fact that you do not have a carbonyl peak is something that should probably be addressed. For NMR, you will have 5 columns. Start with a chemical shift. Tell me what type of hydrogen that is associated with. Tell me what the splitting pattern is, the integration, and then make an assignment. To do assignments, to assign a particular peak to a particular hydrogen, you do have to have a structure in which unique nuclei are labeled. Equivalent nuclei will bear the same label. So by symmetry, these hydrogens are equivalent, so they both have the same label. And that structure should be near the table, so someone can look at the assignments you make in your table and quickly look at the structure as well to see what those assignments are. Here we have a partial table for this structure that's filled in. We have a peak at 6.8 ppm type. So this is in the aromatic region, so it's an aromatic hydrogen. 3.75, this is the alkoxy region. 2.74, this is benzylic, and so we would identify that hydrogen type. Splitting, if you remember from my discussion earlier of NMR, the 6.8 peak was a multiplet, or if you recognize it as a doublet of doublets, you could actually put DD for doublet of doublets. But then put the integration. Integration should be whole numbers. Don't give the numbers that are on the spectrum, since those will be fractional typically, but they should be very close to a whole number. And then give the assignment. Is this hydrogen A, hydrogen B, hydrogen D, whatever? Again, when you discuss it, the text should be able to stand independent of the table. So if I delete your table, I should still be able to read your text and understand what is there. So tell me, there is a peak at 2.7 ppm. The peak is a septet. It integrates to 1 hydrogen. So from this, I know what is present in your spectrum. Then tell me what it means. This is the benzylic region. The septet splitting indicates this methine has 6 neighboring hydrogens, suggesting that there are 2 neighboring methyl groups. And then draw the conclusion this points to an isopropyl group bonded to an aromatic ring. You could also say that this is hydrogen D. This corresponds to hydrogen D. So you're making that correlation as to which hydrogen you are looking at with this particular peak. But always start with the data. Start with the spectrum. What is the chemical shift? What is the splitting? What is the integration? And then go from there and draw your conclusion from that. If I see an analysis like this, hydrogen E is a saturated methyl group with 3 hydrogens. It has 1 neighboring hydrogen, hydrogen D, so it will be split into a doublet. There are 2 equivalent methyl groups, so the total integration will be 6. He is thus part of an isopropyl group. You will see this. Why? What is wrong with this analysis? Hydrogen E is indeed a methyl group. It is indeed next to a CH, so we would expect it to be a doublet, and there are 2 hydrogen E's, so we would have a total integration of 6. So what is wrong with this analysis? Think about what you are supposed to be interpreting. You are supposed to be starting with data and the data is your spectrum. At no point does this analysis actually describe the data. This person is interpreting their conclusion and from that drawing data. That is backwards. The structure is your conclusion. Don't start with your conclusion and then try to tell me what the data should look like. That's working backwards. And this runs into a problem if your data and the conclusion don't match. And I see this on a regular basis. I've had a student in the past who accidentally opened his butyl benzoate spectrum, the one that was used for the NMR assignment, instead of the Wittig spectrum, and started trying to make his spectrum fit the product that he had. And of course it didn't fit, but he tried to force it to fit anyway. He did recognize there were problems, but if he had actually interpreted the spectrum he had, he probably would have realized that he was looking at the spectrum of butyl benzoate. He would have recognized his error, and he would have then analyzed the proper spectrum. I've also seen cases where students have drawn the wrong structure, and again, based on that structure that they drew, tried to make the data fit. If they had started with the spectrum, looked at the spectrum they have, and started doing an interpretation, they probably would have realized again that they have the wrong structure, and they could have corrected that. But because they tried to force their data to fit the conclusion, they ended up with a poor discussion. It also meant that their chemical equation, which was written wrong because, again, they have the wrong structure, was not corrected. And, of course, the calculations would have also been wrong since, again, they have the wrong structure. Always start with the spectrum. Analyze what you have, draw the conclusions, and then try to draw a structure from that. Always use your data to draw conclusions. Start with the spectrum, analyze it, and see what structure you get. Don't start with your structure and then try to tell me what the data should look like. Tell me what the data are that you actually have.